Well, good day, it's Charlie, ZL2CTM. Well, I'm about to disappear on another business trip, so I thought I'd do a video this morning just sort of catching up on where I've got to with this. I was tempted to call it what not to do, but I think it's probably better to say Rome wasn't built in a day, so let's leave it there and we'll have a look at a few things. Okay, so just to recap, looking at this for the main power amplifier. So two LDMOS devices, the BLF1043. Interesting enough, those are UHF devices. They do say in the spec sheet that from 800 megahertz onwards, but then they talk about elsewhere in the same spec sheet HF through to those sorts of frequencies. So anyway, that's what I'm just playing around with. They were reasonably inexpensive, so it was a nice way of sort of giving it a go. Push-pull arrangement here. What else? Pretty stock standard really. That 39 ohm resistor is guidance that comes out of the spec sheet. So they were using 39 ohms. They were having a quiescent current for a lot of the graphs in the spec sheet of 85 milliamps. So that's what I've decided to do for that one. T1 there is an FT50-43, slightly larger one. And that's 12 bifilar turns. In this particular case, I don't have two caps, which we'll see before. Just got one cap sitting off the common point there. Running into a 50 ohm load. We'll look at T2 in a sec. On the input side, this matching network here. Let's have a bit of a chat about that. The preceding stage was the NE592. Now the NE592 spec sheet suggests that the output resistance for the NE592 is 20 ohms. Now for the input impedance for the LDMOS, the only thing I can probably go by is, if we just sort of run across to here on the spec sheet, is this one here, which is entitled input impedance as a function of frequency. But unfortunately the frequency, of course, because of the way the device has been made and what its application is, from 800 megs through 1000. But interesting, the resistance line there is is flat, sitting at 1 ohm. So all things being equal, I've just assumed then that it's going to be 1 ohm right down in 7 megs, which is the frequency of operation for this one. The reactive component there is dropping and dropping and dropping between 1000 megs there and 800, and I haven't endeavoured to try and extrapolate that out. So certainly not the most accurate way of doing it, but so be it. So I initially, from an impedance matching point of view, went to solid state design for the radio amateur and looked at the LC matching network here. Also had a bit of a look at the Pi one, but just decided to stick with the two reactive components there. This works, this particular setup here, when R2 is greater than R1. So in this particular orientation, R2 is our 20 ohms coming out of the NE592, and then R1 is the input to the LDMOS, which I'm just going to assume at this stage is 1 ohm. So the inductive component there, I'm going to have this as a low pass. XL, that's the formula there that comes straight out of SSDRA, which is R1 squared, or R1 times R2 minus R1 squared. Substituting in our values, we come out with 4.36 ohms. And we know that XL equals 2 pi FL, and our frequency of operation is 7.1 megs, therefore we can rearrange that formula there to make the inductance the subject, and then solve for it. Comes out at 97.71 microhenries. I'm going to use a T37-6, which is suitable for its 3 to 10 megahertz range toroid, and that will work out to be 6 turns is roughly at 97.71 microhenries. So that's what we use there, and that's what we see here. Just a little yellow, yellow cord 37-6. Right, so that leaves the other component. And now, interesting enough, the SSDRA has for working out its capacitive reactance, R1 times R2 divided by XL, which we can solve by substituting in our values. 4.36, of course, we've just worked out before, comes out at 4.59, and I'll come back to this one in a sec. We know that our capacitive reactance is 1 over 2 pi FC, so again, substituting in for 7.1 megs, rearranging to make our capacitance the subject, comes out at 4.88 nanofarads. And I'm not going to try and come up with a combination of parallel and series devices. I'm just going to, for the sake of testing, just use 4.7 nanofarads, which is pretty close. So in other words, a 4.72 on the side of the cap. Now, EMRFD, so experimental methods for RF design, same or very similar authors between these two publications here. For the parallel reactive device, or XP, they have a slightly different formula. So they have R1 squared plus the series reactance squared divided by the series reactance. And interesting enough, if you use that formula, you come out with the same number. But I thought it was just an interesting observation between the two publications with virtually exactly the same text, because a lot of the publication, this was the earlier publication here, and a lot of the wording is just ported straight across to the more recent publication. But in this particular case, they had a different formula. But either way, those are the two values there, our inductance and our capacitance. So that's what I tried to use for that, just going back to here again, for that impedance matching network here between the input, so again our driver, and the input to those two LDMOSs. Now for T2 here, it's my understanding, and please correct me if I'm wrong here, for a push-pull amplifier here, our Z out is VCC squared over 2 times power out. Now these LDMOSs here are good for 10 watts, so I'm going to basically just say let's go 10 watts times 2 for a push-pull. So 2 times, if we now use this formula here, 2 times 20 watts under 13.8 squared. I'm just going to try 13.8 for a start. Comes out at 4.761 ohms, which I need to transform across from our 50 across this way. So, and the other thing I'm going to try here too, which is something a little bit different, is on the primary side, on this side here, I'm just going to have a single turn, and then on the secondary side, just look at 2, 3, and 4. So with a single turn, our turns ratio then n equals 2, n equals 3, n equals 4. So therefore our impedance transformation is 50 ohms divided by n squared. So it comes out at for two turns is 12.5, 3 turns is 5.6, and 4 turns is 3.125 ohms. So I'm just going to have a look at that 1 to 3, so 5.6 ohms. So coming back to our original formula here, VCC squared over 2 times PO, rearranging that to make our power out the subject, and we can substitute in our known values. So 13.8 squared divided by 2 times what we've now worked out here, 5.6 ohms, comes out at 17 watts. Interesting enough, if you were to use the 1 to 4 turns, which would transform 50 down to 3.125 ohms, then you're supposedly getting around 30 watts, which would exceed our maximum power rating for those two devices there. So I'm going to stick back onto that 1 to 3. I guess a question, and I don't know, and I haven't been that easy to find the answer, is that the correct impedance that I need to be producing here, or do I need to divide that by 2 again because of that centre tap there, or the common earth? Is that being presented across both of those, or just across the single? So I think this is correct, but like I say, if I'm not, please sing out. Rightio, so the actual amplifier itself, I did try the impedance matching network. So I did have those two inductors there in series with the input. So I guess it's probably worth just very quickly going through the circuit here. So we've got our just ignore this transformer for now. I've got our input here. There's going to be the capacitors to earth, and then the series inductor, those two 37-6 toroids. and then the two biasing networks on either side. So those two 39 ohm resistors, and then sitting on, as per the schematic, two 10 turn 10 k ohm resistors that are then providing from this 5 volt regulator a variable voltage, DC voltage, to the gates of those two LDMOS devices. Interesting enough, I thought from reading about these LDMOSs here that I thought you soldered the flange to what is the ground plane, because that flange is the source, and then typically you have plated through holes that then transfer the heat to a heat sink that's sitting underneath the board. So I thought that I would do things slightly differently. I would have them sitting here. I would solder the flanges on either side to the ground plane, and then use this copper board here to wick away the heat. And then if there was a requirement, I was going to have a heat sink here and here, sitting vertically. When I came to actually solder them on, what I thought was going to happen didn't actually happen. I do have, I believe, a good good connection between the sources and the ground plane, but I was expecting the solder here and here, there and there, to actually wet up and adhere really nicely to the flange, but that's not actually the case. I think there is some wetting or some soldering there between the flange and the earth, but it's not what I expected. So yeah, clearly I'm not using them the way they were intended, but what I thought was going to work didn't actually work, so never mind, that aside. Right, so just want to talk about the biasing. So we talked about 85 milliamps was the quiescent current through these two LDMOS devices. So what I did there, on the VCC line coming in, and it's actually still in place, just if I just move it up there, is that 1 ohm resistor. So I've got the 1 ohm resistor in series with our current coming in to the amplifier, and I'm just measuring the voltage across it to work out how much current's going through it. I'm doing it this way because I've had a bad experience before where an amplifier took off and I blew the fuse inside the ammeter. So it's just a way I've been sort of doing it more recently, just to, I guess, give myself a little bit more safety margin there in terms of not blowing that fuse. It's not a hard shit to replace, but it's just another way of doing it. So anyway, so I'm using that voltage drop to determine how much current is coming out of the actual amplifier. So with no signal coming in, and these two variable pots set to 0 volts being applied to the gates, one at a time, started to increase that voltage, and then measured the output current, and then set that to 85 milliamps. Left that one alone, come across to this side, did exactly the same thing, and then increased the current up to another 85 milliamps. So that's how I set the quiescent current for those two devices there. Right, so that was the quiescent current. That's right. What I did find, so that's the other amplifier we had in the previous video, the NE592. When I had that matching network between the two outputs to the inputs of this, the performance was just not there at all. There was just no real amplification, and really just wasn't driving these in any way, shape or form to anywhere near that sort of 17 odd watts or so. So what I elected to do then, just for experimenting sake, is I desoldered the two inductors, replaced them with a coupling capacitor, just to make sure that any transformer on this side is not going to short the gate biasing voltage to earth or to each other. And then for testing purposes, put in its place an arrangement where I've got a center tapped primary, or secondary I should say, transformer here. So the secondary is centre tapped, and then the primary is through here. Didn't attempt to do any kind of impedance matching between the 50 ohm signal generator and the 1 ohm supposed input to these two LDMOSs. I just kept it as a 1-to-1. So 2 turns on the primary, 2 turns on the secondary, tapped. Centre tap there, so we get the anti-phase driving for the push-pull amplifier. So what I do now is just have a quick look at, we'll scope it up, and we'll throw in a drive signal, and we'll just look at what's coming out, and then sort of make some observations on that. Like I say, and I've said it many times, and I'm going to say it again now, I'm no expert in any way, shape or form in this. I just try and work out what's going on from the textbooks, and then have a bit of a play. So at the moment, the test setup is our input signal generator there. That's 7.1 megahertz. It's currently sitting on 1 volt peak to peak coming in. Our switch is currently off, and we are measuring our voltage across that 1 ohm resistor, and then up on the scope we're looking at the output there. So if we were just to look at channel 2, so channel 2 is our voltage on the gate coming in, so it's just looking at one of the outputs of that centre tapped transformer. We can see there that in this particular case we will just stick on, say, I want to go 20 volts peak to peak, which is the maximum I can get out of the SIGGEN. We're getting there, this is on ×1 if I recall, yes it is. We're getting there 1, 2, 3, 4 volts peak to peak. The output side is on channel 1, so go back to channel 1, and if I was to keyer up, so that's what we're now getting on the output. So that is 1 volt, it's switched on ×10, so 10, 20, so 20 volts peak to peak. And I'm just going to shut it off there because I am reasonably quickly starting to overheat these two devices here. So if I was to turn that back on again, I need the good old finger check. Now it takes a little while, but we're getting to a point there where those are too hot to touch. So I'm clearly, and I'll admit it, not using these devices correctly in terms of mounting them and having that heat sink wicking away. There is a bit of heat, there's certainly some heat coming out, but nowhere near enough to use those in that particular configuration. But interesting enough, so if we were just to look at the gain, so if my calculations are right, that was a gain of about 13 dB with an output wattage of, what do we say there, so it was going to be roughly 20 volts, so 0.7071 times that. We'll square that, 50 divide, comes out at 4 watts. So only producing there 4 watts of output power in that particular configuration. Unfortunately, that's all I have time for before the business trip coming up. So I can't really do too much more. I'm not entirely sure what I want to do when I come back. I'm clearly not using these correctly. I'm certainly glad I got them, and I'm certainly pleased for that advice that came in on some comments on a video back. And I thought the way I was going to be able to mount them is just not not correct. And given the available resources I have here at home, I'm probably not going to be in a position to be able to use these correctly. But interesting enough using it nonetheless. And I guess the only other thing of interest sake was the current I'm drawing through it is now 0.76, so that's 0.8 amps, that's 1 ohms, so that's interesting enough there, so not pulling a huge amount of current. Right, so I think that's probably all I want to say here. When I do get back, I'll have a think about what I want to do for the power amplifier. There were some other things I wanted to do, or other circuits I wanted to look at when I first came into this particular project. One of them was to look at this old IC720 amplifier board here, maybe see if these two devices are still serviceable, and then look to use those. Or or maybe use some other kind of RF transistor, or maybe even just a BD139 push-pull amplifier. I don't know, I'm not quite sure where I want to go there. I've got a couple of other sort of solid-state amplifier blocks from a couple of other old radios, which might be interesting to try and to use as a hybrid, work out what kind of gain is needed for those, and then give those a go. Anyway, so that's pretty well where we got to. So like I say, I was originally thinking about how to sort of approach this particular video. You know, one could argue this is what not to do. You know, Rome wasn't built in a day. You know, this is what I tried. This is sort of the pitfalls I got to. So, you know, if that's of use to people and can be squirreled away as tribal knowledge, then hey, that's great. Right, I'm going to say 73s, and we'll see you in a week or two's time, and we'll continue playing around with this amplifier. Okay, cheers all.